Hello everyone and welcome to Lesson 4 of the AP Calculus AB/Calculus 1 summer course. In case you're wondering up until this point why I called it the Calculus AB/Calculus 1, it's because if you're in high school you probably call it Calculus AB, and if you're in college you probably call it Calc 1. So it's the exact same thing. Actually it's funny, in college typically you don't go as far as Calc AB, and I'm not going to explain what I mean by that because I could be wrong, could have been different from my high school than your high school, could be different for colleges. But basically what I've noticed is in high school you actually cover more material than in college, and that makes sense if you think about it because basically what college Calc 1 is the exact same course that high schoolers take basically, except they have to do it in half the time because you have to be done by the winter. While for Calc AB in high school you have like the whole year to do it, so it's a lot more time. So anyways, with that we're going to get started. So we're going to get started with the chain rule. And chain rule is basically the only rule left of derivatives we have to talk about. I mean, there's definitely more rules, but at least in terms of the basic rules, chain rule is the last one. And I say basic in air quotes because it actually is probably the hardest of all the rules, but that's okay because I'm here and I'm teaching it and you'll understand it, hopefully. Definitely if you practice, you're going to understand it. That's a promise. So first, I want to talk about when you use chain rule. We use chain rule when you have a rule inside another rule. And I'll explain what I mean by that. Let's just look at a quick example just to see what it looks like. Let's say you have the function 2x plus 4 to the third power. This is a combination of two rules. Number one, you have the outside rule, which is the cubed, and then you have the inside rule, which is the derivative of 2x plus 4. And then the question is, well, how do you deal with that? How do you deal with functions when you have a rule inside of another rule? And basically, I go over this kind of complicated explanation, and I say these rules of the chain rule, and I go over f of g of x, and blah, 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 blah. In my opinion, this is a little overly complicated. Technically, this works, but this is kind of like the advanced formula, which I guess is helpful to know, but I'm going to explain it the easy way first. And we're going to be using I call it the easy way, because why would I teach the hard way? Anyways, the easy way to take the chain rule is to take the derivative of the outside rule, okay, and then multiply by the derivative of the inside rule. And I'm going to give you a second to write that down. But basically what I'm saying is if you recognize the outside rule and the inside rule, then what you can basically do is say, hey, I'm going to take the derivative of the outside rule first and then multiply by the derivative of the inside rule. And when you look at it from that perspective, it's really not that bad. So let's go ahead and look at some examples. First one, y equals the sine of x squared. All you need to do is first of all recognize what's the outside rule and what's the inside rule. The outside rule is going to be your sine, and the inside rule is going to be your x squared. So all I'm going to do is I'm going to ask myself, what's the derivative of sine? And if you remember from last week, you know it's cosine. So y equals the cosine of x squared. Notice I'm keeping x squared. A lot of kids do this. They'll take the derivative of sine and get cosine, and then they'll take the derivative of x squared and they'll write cosine of 2x. And that's not right because you don't do the derivatives both at a time. That's not what I wrote down earlier. I said you take the derivative of the outside, and now we're going to multiply by the derivative of the inside. Derivative of x squared, 2x. There you go. There's your answer. If you want to write it a little nicer, I mean, you can write the 2x out in front, but it's the exact same thing. I'm not even going to make that necessary. I'm not going to make that a requirement. Both answers are completely fine. And that's all we do. Derivative of the outside times derivative of the inside. By the way, at this point, I'm assuming you know the derivatives we talked about from last week. If you're not like super 100% confident, that's okay. But if you're like 70% confident, that's all I'm asking for you today. And if you're not there yet, then basically you need to review last week's derivative rules and review those, because I'm definitely going full steam ahead. as you will find out. So for the next one, y equals x, the square root of x squared plus 4. For this one, if you remember what we do with square roots, I'm just going to rewrite this as x squared plus 4 to the 1/2 power. Now we see the outside and inside rule. Outside rule is 1/2 power. Inside rule, x squared plus 4. What do? I deal with the outside first. And that's a power rule. And the power rule just says bring the 1/2 out in front times the original x squared plus 4. Don't change that. Keep it the same. And don't forget what's 1/2 minus 1, because the power rule says subtract 1 from the power. So 1/2 minus 1, that's negative 1/2. Hopefully I don't need to explain that. So negative 1/2 power times the derivative of x squared plus 4. That is 2x plus 0, or I'll just write 2x. Now for this one actually can be simplified quite a bit. First of all, I want to say I'm completely fine, especially for like this is the first time we're ever using the chain rule. I'm completely fine with this as your final answer. But if you are feeling adventurous and you want to try simplifying this, then we need to try and combine like terms first of all. In other words, the 1/2 and this 2 cancel out because 1/2 times 2 is just 1. The other thing I want to say is if you have a negative 1/2 power, remember a negative 1/2 power, negative means it's in the denominator, 1/2 means square root. In other words, x squared plus 4 is now going to be a square root in the denominator. I also just realized for like these past two problems, I was not using good notation. Should have picked up on that. Not you guys, I'm saying me. Although you should have too, of course. It's your fault. Anyways, I forgot to write y prime. I just wrote y. That's wrong. Yeah, this is all y prime because it's the derivative. Now, of course, you could also write dy dx, which is also correct, but y prime is generally preferred among students, so I'll write y prime as well. Anyways, what I was saying is what's left in the numerator? There's only one thing left. It's this x right here. And in the denominator is the square root of x squared plus 4. Again, this is like the super simplified version. If you have the above version before I canceled everything out like this, then this is okay as well. I don't really care. Any questions on that first page? Okay. Don't worry, we're going to see a lot more examples of chain rule at the end of the lesson. But for now, we're going to go over the worst case scenario. Oh no. The worst case scenario is a chain rule within a chain rule. We can call this a double chain rule, or as I like to call it, a 2 chains. And that is a joke, because I am definitely not okay to say that. But anyways, basically what this is going to look like is we have a function inside of another function inside of another function. If you've ever seen the movie Inception, which at this point is probably too old of a movie reference for you guys, but if you have seen it, fantastic, you know what I'm talking about. If not, it's just a movie where people would go into dreams inside of another dream. It's a cool concept. Anyways, I like the movie, but that's not the point. The point is, all you're going to do is say y prime is the derivative of the very outside rule. The very outside rule is the cosine. And what's the derivative of cosine? Hopefully remember, it's negative sine. So watch this. Negative sine of sine x cubed. I'm not changing anything in the middle. I just took the derivative of the outside. Next, I need to take the derivative of the middle. What's in the middle? In the middle is my sine. So next, I'm going to multiply by the derivative of sine, which is cosine. So the cosine of x cubed. And then finally, I have the derivative of x cubed, which is going to be 3x squared. So if I were to just color code this, let me just color code it for us real quick. Let's say blue is the outside rule, green is the middle rule, and red is the innermost rule. Then basically what I'm saying is this is the blue, this is the green, and this is the red. And hopefully that makes sense now. I should have done red, white, and blue because it's the 4th of July, but I don't see how you're going to see a white marker on white paper. So we're doing red, blue, and green, probably reminiscent of, I bet there's some country with these colors, so we're going to say it's their Independence Day too today. And by the way, can you simplify this? The answer is no, because there are no like terms. And if you disagree with me, then you're wrong, but you're more than welcome to speak up so I can say how wrong you are. No takers? Okay, excellent. And with that, I don't know why I gave this much space, but it was just like a one-line thing. I guess if you do it the long way, because I mentioned earlier there is a harder way of doing this, which I do not do. I like the easy way. And you probably only need to know the easy way for school, so I don't really want to teach you the hard way anyway. Okay, next is differentiability. What is differentiability? Well, differentiability is basically a fancy word for where the derivative exists. If we say a function is differentiable everywhere, then that just means the derivative exists everywhere. And hopefully that makes sense. And then the question becomes, well, where does the derivative not exist? And there's quite a few answers we have. The first answer is a corner or a cusp. This is a corner, which you've known if you've ever lived in a house before. And this is a cusp, which you've probably never heard of before because I haven't either. A cusp is just a corner, but for rounded lines. So basically, if you ever see, I don't know, like really fancy architecture in your school or in a building, the chances are if it's curvy, then it's probably a cusp, not a corner. And you can tell everyone around you that, and they'll just ignore you like they do me. But anyways, the reason why it's not differentiable there, why the derivative doesn't exist there, is because what's derivative anyway? Derivative is slope. In other words, the slope doesn't exist. If I were to ask you what's the slope at that point right there at the corner, you can say 0 because it looks like it's got to be 0 at some point, but technically we don't actually know what the slope is. It's because the slope, if you count it, like let's say the blue line here is this way and the red line here is like this way. Well, you got like two different slopes intersecting at like a perpendicular line. In other words, the slope is undefined, I guess you could say. And I guess you could say indeterminate, not really sure about that. But either way, you can definitely say it's not differentiable, and that's basically what we're saying here. And the same is true for the cusp. Any questions on that first point I'm making? Okay. Next, the next point where it's not differentiable, any discontinuity or an endpoint. So basically, we would say it's not continuous here. It's not continuous right there. It's not continuous right there because that's a vertical asymptote. I know I didn't draw it, but it's a vertical asymptote. And then here, these are endpoints. In other words, the slope actually does not exist at endpoints. Everywhere in the middle, that's perfectly fine, but not at endpoints. And you may be wondering, why is that? Because technically, in order for a slope to exist, there needs to be a slope to the left and to the right of it. That's like the technical definition of differentiability. So if you just want to memorize as little as possible, like I would recommend for the summer, if you see an endpoint, it is not differentiable. Next, vertical tangents. This is the last example we'll talk about today. I'm sure there's more examples where it's not differentiable, but these are the major ones that we see. So a vertical tangent line, this is going to be confusing. This is not an asymptote. This is not an asymptote. This is a vertical tangent line, which looks identical to an asymptote, but basically what it's saying is the slope is infinity. What does that mean? It means that you cannot have a slope equal to infinity. If your slope equals infinity, that's impossible. Remember we said earlier for limits, limit doesn't exist when you have infinity? And now you're thinking, well, when would this happen in real life? Well, for instance, this function right here, this is the cube root of x. And if you take the derivative of the cube root of x, I'm just going to do it for us. You don't have to do it. You can prove it if you want. But it's going to be 1 over 3 times the cube root of x squared, which is like really complicated, and it's actually not that complicated. It's just a power rule. But if you plug in 0 right now, what are you going to get? You're going to get, I'm just going to tell you, you're going to get 1 over 0, which is not indeterminate, it's undefined. And if you were to plug this in a calculator, it would say error, and that's why it's not differentiable. Oh, and 1 over 0 is technically infinity in a lot of circumstances. And if you don't understand why, don't worry about it because that's not the point of this class, okay? Just take my word for it. Anyways, we've seen all the examples now, but how are we going to determine if something is differentiable or not? It's a pretty easy process. We just follow these 4 steps right here. The first step is really long, Basically, all I'm saying is it continuous? And if you remember, we had like a 3-step process last week to determine if something was continuous or not. And that's pretty annoying because this is just the first step of differentiability. So just to make this lesson go as smoothly as possible, I'm probably going to be a little efficient and a little fast. I'll probably skip some steps with the continuity, but you'll agree with me that it will be continuous. Step 2, find f prime of x, the derivative. Pretty straightforward. Step 3, use the same continuity rules that we did for continuity to prove that f prime of x is continuous. Oh, and I should probably say what the continuity rules are because you're probably wondering. Continuous, you have to check 3 things. Number 1, you have to say f of c exists, where c is just some number, the point you're testing. Okay, so like c could be 2, 5, 1 million, whatever. Okay, that's the first check. The second check you need to do is you need to say the limit as x approaches your number, c, whatever number that is, f of x has to exist. If you remember, that's where we check both the left and the right hand limit. In other words, limit as x approaches c from the left and limit as x approaches c from the right, and they have to equal each other. And then the last check is that your value is equal to your limit. And this is just a review from last week. Now, basically, I'm going to skip a lot of these steps because it takes a really long time and it's not necessary most of the time, and I'll explain why. But basically, what I'm saying is, especially if you have a piecewise function, which if I scroll down just a little bit, yeah, that's a piecewise function. All we need to do is make sure that the top function equals the bottom function. I'm going to use like a shortcut that will work for this summer, but might not work for your calculus class next year. You have to ask your teacher. Anyways, I'm assuming you're done writing. Oh, and then step 4, if there is a discontinuity in f prime of x at x equals c, then f of x is not differentiable. Yeah, that's basically saying it's not continuous, not differentiable. Okay. So for this one, negative x and x, when x is less than 0 and x is greater than or equal to 0, and we're checking the point x equals 0. So step 1, is it continuous? All I'm going to do is I'm basically going to plug in 0 for the top and the bottom. So for the top, it's negative 0 when I plug in 0. And for the bottom, it's just 0. And I think 0 equals 0. And just for the sake of this check. Okay, it's definitely going to be continuous, I promise. And if you go through that whole 3-step process, you do the limit and you do the value, you will agree with me. Okay, now if you want to find out if it's differentiable, we need to take the derivative. Maybe you've never taken the derivative of a piecewise function before. That's okay. I remember my first time. Anyways, all you got to do is take the derivative of the top, the derivative of negative x. Again, this is a coefficient rule where the coefficient is negative 1. So that's negative 1 for the derivative when x is less than 0, and then positive 1 when x is greater than 0. Now you'll notice here I'm not going to say greater than or equal to. Why not? I see greater than or equal to right here in the piecewise function. Well, the reason why I'm not saying equal to yet is because if I say equal to, then I'm saying it's differentiable, de facto. In other words, I don't know if it's differentiable yet, so I can't say equal to yet. They could have 2 different slopes, and then it's no longer differentiable. Now, how am I going to determine if it's differentiable or not based on this derivative? It's simple. Does the top equal the bottom at x equals 0? Well, does negative 1 equal 1? No, of course not. So it is not differentiable. Not differentiable. And that's going to be the answer for this one. And let's just say hypothetically they were equal to each other. Then fine. All I would change it, I would write differentiable. And then finally I would write the equal sign here, because now I can say it because it's differentiable. But since it's not differentiable, no equal sign, because that would technically be wrong. And is that a big deal? No, I don't care. I care that you write not differentiable. That's the most important part. Any questions on that one? No? Okay then. So we're going to move on. We're going to be doing more examples of chain rule and differentiability at the end. But first we need to talk about the mean value theorem. So the mean value theorem, I think it's going to make more sense to talk about the next page first. What does the mean value theorem look like? So this is like the next page. You can turn to it. I'd recommend filling it out. Let's talk about what the mean value theorem says. So the mean value theorem, one of the more important theorems in calculus. You're definitely going to see it next year, I promise you that. Let's just pick 2 points at random. Let's choose this point and this point. The points do not matter. I can choose any 2 points on this graph. Does not matter. Now I'm going to draw a straight line connecting these points. Like that. Perfect. Okay, I got a straight line connecting these points. Now, here's what the mean value theorem says. This red line has a slope. Hold on. This red line has a slope of whatever. Okay, clearly it's a negative slope. Maybe the slope is -1. I don't know. But what the mean value theorem says is there must be another point on this graph in black that has the same slope as the red line. So let me just pick a point at random and see if it has the same slope or not. I'll choose this point right here. And the slope right there, it looks like it's about like that. Don't actually write down what I'm writing. Hopefully you didn't, because this would be wrong. Why? Because the slopes are not the same. Like clearly the red slope is not as steep as the blue slope. The blue slope is even more negative. So in other words, that's not a good point to choose. The correct answer is this point right about here. It's an estimate, I'll admit, for the graph. Okay, once we get to actual numbers, we'll get exact answers. But what I'm saying basically is that this slope right here, if I draw a straight line through it, should be parallel to my red line. And I'm going to assume it is because I theoretically chose the right point. Actually, technically, this one has 2 points where they have identical slopes. If you like zoom in, like super close right there, yep, right there, you'll see I have another point where the slopes will be the same. If you missed that one, I'm not too upset. That one was hard to see. But technically, you have 2 slopes this time. Now, what the mean value theorem says, you have to have at least 1 point. You have to have at least one. If you have 2, great, extra credit. And you'll also know that the only points I'm looking at here are between my 2 points. Typically, you call the first point A and you call the second point B. And technically, yeah, sure, there could be other slopes where they're equal outside of A and B, but I don't care. I don't care. I only care about in the middle between A and B. So that's what the mean value theorem looks like. Basically, if you want to put this in the most basic terms possible, we're going to look at the formula, and then I'm going to explain it. Whoops, wrong tab. And then I'm going to explain it in the most basic terms possible. So let's look at the formula right here. Okay? What this is saying is the slope of the tangent line. Remember, a tangent line is just, that's the blue lines right here. It's where it's just touching it, just barely kissing the graph, just like that. Okay? That's what a tangent line is. You're going to notice you're going to take the derivative, okay? Because that's what f prime of c is. Don't worry about the c. I'll explain it later. And then I say here the slope of a secant line. Now a secant line, f of b minus f of a over b minus a, that was a red line. And that just follows the formula y2 minus y1 over x2 minus x1. That's all this f of b and f of a stuff is saying. It's just the algebra 1 definition of slope. So not that bad. And basically what you're saying is, you're saying where does the derivative equal the algebra 1 slope? That's what you're saying. That's what the mean value theorem says. Oh, and one more very important and crucial piece of information before we actually do these examples. If you look right here, there are 2 conditions that must be met before you can even use the mean value theorem. So we kind of went in reverse order, but technically you should always start with this. Number 1, your function needs to be continuous on the interval a to b, and you must be differentiable. Remember, differentiable means the derivative exists on the interval a to b. You'll notice that this is the closed interval because it's brackets, and this is the open interval, meaning that the closed interval can include a and b, but the open interval does not have to include a and b. I'm not going to explain today why that's true because it's too technical. It should never come up. Well, maybe it will because I'm probably a jerk in the homework. But assuming it doesn't matter, we're not going to worry about that, okay? Don't worry about the closed and the open interval. It's not going to matter. And with that, let's look at an example, and then we will go over the rest of the example problems for this week. So, example. Find the point x equals c, which satisfies the mean value theorem for the function f of x equals x squared over the interval -1 to 3. So before I even use the formula, I need to prove that it's continuous and differentiable over that interval, -1 to 3. The good news is, where is f of x equals x squared continuous? Well, it's continuous everywhere. How do I know? I know because give me a value for x that I plug in this calculator and it says error. Like for instance, if I say 3 squared, will my calculator say error? No. If I say -100, my calculator will not say error. Basically, the only thing you have to watch out for is you have to watch out for square roots in the denominator. I'm sorry, I combined those two. Square roots, like negative square roots, and 0 in the denominator. Those are the only two things you have to watch out for the most part. And since x squared doesn't have a denominator, it doesn't have a square root, it's continuous everywhere, which is great. And now I have to say, where is it differentiable? Well, to say where it's differentiable, I got to take the derivative. So the derivative is 2x, and 2x, that's continuous everywhere also. But I wouldn't say continuous, I'm going to say differentiable, because differentiable is the derivative, and that's what I'm talking about. Okay, so it looks like we're good. Check, check. I've satisfied the two conditions for the mean value theorem. Now I get to use the formula, which says f prime of c equals f of b minus f of a over b minus a. So the left side's already done for us. I'm going to write, well, not 2x, I'm going to write 2c. Yes, x and c are basically the exact same thing. Why do they use c? I don't know, but on the AP exam and a bunch of times in different calculus courses that I see across the country, they use c instead of x for mean value theorem specifically. I don't know why, but they do. Okay, now, f of b and f of a, this is the same thing as y2 minus y1. All you gotta do is plug in 3 and -1 into your original function. So in other words, f of -1 plugging -1 into your original function is -1 squared, which is +1. Now for f of 3, you're going to say 3 squared, which is 9, and there we're pretty much done. So f of b is 9 minus f of a, which is 1, divided by 3 minus -1. Be careful there, that will be a double negative. So I'm going to continue on the other page. We have 2c equals numerator 8, denominator 3 plus 1 is 4. So it looks like 2c equals 2, c equals 1. There's your answer. Oh, and by the way, if you ever got an answer, like this is just one answer, technically you can have more than one answer, but if you ever had 2 answers or 3 answers or whatever, you got to make sure all your answers are within your bounds. What were my bounds? -1 to 3. Is 1 in between -1 and +3? The answer is yes, of course it is. So make sure you're checking your answers there. For instance, if I got +5 as an answer, I'd have to cross it out because that's not in my bounds. And that's okay. It's just the wrong answer. Don't worry about it. Either way, c equals 1 is the answer. Any questions on anything related to the mean value theorem? No? Okay then, so for the rest of the time today, for the next half hour, we're just going to be doing example problems of everything we just talked about today. How exciting. Okay, number 1, we got some chain rule. Use the chain rule to find the derivative of the following functions. The first one we have is sine squared of x. I'd recommend rewriting this first. I'd recommend writing this as sine of x squared, because now you clearly know what the outside rule is and what the inside rule is. Because remember, chain rule is derivative of the outside times derivative of the inside. So the derivative of the outside, f prime of x, equals derivative of squared, you pull the 2 out in front, and then times, remember, don't take the derivative of the inside yet, just write sine x. And now that's raised to the first power, which technically doesn't really matter, but I'll write it there anyway. And now you multiply by the derivative of sine x, which is cosine x. So you can simplify this if you want. You can write 2 sine x cosine x, and that's a beautiful answer. But if you didn't simplify it, if you kept this, I'm okay with this as well. Any questions there? Okay, good. The next one is harder. We have f of x equals the square root of x cubed plus x squared plus 2. Okay, I'm going to give you a tip for this first one. The tip being, first rewrite this as x cubed plus x squared plus 2 to the 1/2 power. And now I'm going to give you a minute. This is not the derivative, but I'm going to give you a minute now. I'm going to let you solve this on your own. And if you can't get it, then too bad. I'm going to give the answer. So go ahead. And if you're watching the recording, you can just pause the video. And time's up. So hopefully the first thing you did for the derivative was you realized it was the power rule outside. So you take the 1/2 out in front. You rewrite x cubed plus x squared plus 2. That's then raised to the 1/2 minus 1 power. 1/2 minus 1 is still negative 1/2. That did not change from half an hour ago. And so it is negative 1/2 power. And then you multiply by the derivative of the inside, which is going to be derivative of x cubed plus x squared plus 2 is 3x squared plus 2x. Close parenthesis, because derivative of plus 2 is just 0. So there's our answer. This is perfectly acceptable. And if you really wanted to impress me, then you would have wrote it like this. Because what's in the numerator? Just 3x squared plus 2x. Technically, the 1/2 is in the denominator. And this whole thing to the negative 1/2 power is a square root in the denominator. So if you really were feeling itchy for ambition, then you would have wrote 2 root x cubed plus x squared plus 2. And that would be correct as well, although I don't care. No one likes to show off anyway. Unless I'm showing off, then everyone loves it, because everyone loves Dan the Tutor. Any questions on that one? Okay. The next one will be, the next two actually, these are going to be double chain rules. How do I know? Because, golly, you have an outside rule, which is the 4/3 power. You have a middle rule, which is this thing. And then you have a very inside rule, which is the x plus 1. So this is a double chain rule. And if you remember what I do for double chain rule, is I'm going to take the derivative of the outside first, which is the blue. So pull the 4/3 out in front. And I know a lot of you want to do this on your own, and you're saying, no, Dan, pick me, pick me. No, I will not. I will not. That's not the point of this. The point is for me to be awesome and for you to become master of this during the homework. So you'll have plenty of opportunities during the homework to try this. Anyways, it's 4/3, pull the 4/3 out in front. Then in parentheses, the original thing, unchanged, do not touch. Close parenthesis, what's 4/3 minus 1? Rhetorical question, I'm going to answer it. 4/3 minus 1, multiply the 1 by 3/3. It's the same thing as 4/3 minus 3/3. You'll get 1/3. By the way, if you're really bad at adding fractions or subtracting fractions, I am having an Algebra 1 lesson tomorrow for kids, and we're on lesson 4, which is about adding and subtracting fractions. So if you feel like going back to Algebra 1 and reliving the glory days, I will send you a link. And if not, I can just send you the recording. And if you really feel like, you don't need fraction help, then good, because you shouldn't if you're taking calculus. Anyways, that's the outer rule. Next, we have to deal with the middle rule. The middle rule is, and I quote, 3, because it's a coefficient, times power rule on that 2. Bring the 2 out in front. It is then x plus 1 to the first power. And now here's the derivative of the innermost rule. It's times derivative of x plus 1, which I believe is just 1, because derivative of x is 1 and derivative of plus 1 is 0. And then the derivative of the minus 4, that's 0 as well, because of the constant rule. So that should be it. Now, in terms of simplifying this, I don't care. This is way too complicated. I'm not even gonna attempt to simplify this, although I could if I really wanted to. But it doesn't matter. This is perfectly fine. This is perfectly fine. Any questions on number 3? Okay. And number 4, again, I'm going to be leading us through this. Even if you think you can do this on your own, I mean, you can make one small boo-boo with this problem, and you are like roads off. It's like you take a wrong road on like a road trip, and you end up in California when you were trying to go to Chicago. Okay, so I'm going to be doing this one, but it is very difficult. It is a double chain rule. Again, I'm going to be rewriting this because cosecant squared is really, I'm just going to rewrite the whole thing, cotangent of quantity cosecant x squared. So now we see that the outermost rule is the cotangent, the middle rule is actually the squared, and the inner rule is the cosecant. Now the reason why I made this problem so complicated and what it looks like is because if you know the derivative of cotangent, you'll know it's negative cosecant squared, which does show up in the middle. And maybe you're thinking that can reduce at some point. And the answer is no, because it just doesn't, and I'll explain why later. But that's why I made this problem looking so complicated. Anyways, we just have to do the derivative of cotangent, the outer rule. So f prime of x, derivative of cotangent is negative cosecant squared x. Except I'm not going to write x, right? I'm going to write the original cosecant x squared like this. Or if you'd prefer, you can write cosecant squared x like you see right there. Not a big deal. They both work. Okay, that's the outer rule. Next is the power rule in red in the middle. You pull the 2 out in front times cosecant x now to the first power. Okay, good. And then the very last one is the derivative of cosecant x, which I'm not even sure if I'm going to have room to write. I'm going to try and squeeze it in here. Derivative of cosecant x is negative cosecant x cotangent x. And then can this reduce at all? Well, it can a little bit, but you have to be careful. So what can reduce? Let's look at this closely. By the way, if you don't want to reduce, you can just circle this, you're done. I'm happy with that too. Now, the cosecant x here can combine with the cosecant x there. That will give us a cosecant squared x somewhere in the middle. Okay, this cotangent x cannot combine with anything, so just put it at the end. This 2 can go out front, so 2 out in front. A negative sign here and a negative sign here cancels out to make a positive, so that's nice. And the only thing I haven't addressed yet is this thing right here. And the reason I have not addressed it is because you think it simplifies to something, but it does not. It does not because it's not cosecant squared x times cosecant squared x. It's the cosecant squared of cosecant squared x, which sounds really confusing, but this does not combine with anything, I promise you. I'll write it like this. And I know that's different than how I wrote it, like, right there, but it's the exact same thing. This is the most simplified version. I do not care if you write this or the above. They're both right. Yes, it's very confusing. I already said that, but this is the answer. Any questions? Okay, if you do have any questions, you can always email me or post in the comments. Or if you're in the live lesson, you can stick around to the end and I'd be happy to answer your questions as well. Next, let's look at some differentiability questions. Woohoo! So remember, where is the function differentiable? So we have quite a few points right here where it's not differentiable. For instance, right here, that's not differentiable because it's not continuous. Not continuous automatically means it's not differentiable. The next point I see that's not differentiable is here, here, and here. That's a corner. That's a corner. And this is technically a cusp. And you may be wondering why, because one side's straight and the other side's bendy. As long as you have one curvy, bendy side, then it's a cusp. If they're both straight, then it's a corner. Does it matter which is which? Not really. You're not going to see that on the AP exam, or probably in class next year. But I'm just telling you for vocabulary reasons. And then, does anyone else see any points where it's not differentiable? The derivative does not exist.
Yeah, I see one at 2.
2. 2 is actually differentiable, I hate to tell you. But the reason why is because look at the slope. The slope is perfectly, it's fine. It's not changing slope at all, like it does at positive 1 right here. Any other points?
Could be like negative 3.5-ish.
Are you saying this point right here?
Yeah, looks like it might be sloping towards 0.
Yeah, I've got bad news for you. You're 0 for 2 for this problem. Basically, that's just a flat slope. Flat slopes are absolutely okay. Because why are they okay? Because you know the flat slope. The slope is 0 at a flat slope. When we have bad slopes, here's what it looks like. It would look like this. It's coming in at 0, okay? And then all of a sudden it shoots off like this. Because those slopes are not matching. An easy way to look at this, here's how you know if it's not differentiable or not. Imagine you're on a roller coaster and you come across this and you start crying because you're going to crash and die. Okay? Like, look at this. This is not going to work out. But now imagine the roller coaster right here. Okay? It's going down, 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 down. I mean, at the bottom, you're completely fine. You're not dying. Okay, it's just a hill. You're fine. Then you go up. And then you look at that like, oh my god, I'm going to launch and I'm going to crash into that section of the graph. Yeah, hopefully you're not writing this down, because this is just like me messing around with the graph. But hopefully you also see what's going on here. Where it's differentiable simply means the derivative or the slope exists. And everywhere else is where it does not exist. Oh, and by the way, this is the only answers. So the points are x equals -3, which was the discontinuous. You've got -1, which is the first corner. You got 0, which is the second corner. And you got +1, which is the cusp. And that is where the function is not differentiable. Any questions? Okay. Now we just got 2 more problems today. They're both mean value theorem. How exciting. Oh, I'm kidding. Wow, we have 3 problems left. How on earth are we going to finish in 15 minutes? Oh well. So for this one, to determine if it's differentiable at x equals 0, all I'm going to say is this. First of all, you need to prove it's continuous. How do we do that? Let's plug in 0 first into f of x for both of these, the top and the bottom. So I'm saying -0 squared, does that equal 0 squared? The answer is yes. Great, because 0 equals 0. Okay, so it's continuous. We know that. And again, I skipped a few steps, and that's okay, because I'm Dan the tutor and I'm saying it's okay. Now for a differentiable. Remember, you got to take the derivative of this. So f prime of x equals, for the top one, derivative of -x squared is -2x. That's when x is less than 0. And then the derivative of x squared on the bottom is going to be 2x, positive 2x. That's when x is greater than 0. Now, obviously, these two functions are not equal to each other, but that's not the point. The point is you got to plug in 0 for both of these functions, and then is it equal to each other? And why 0? Because I'm asking about 0, obviously. So what I'm saying is -2 times 0, does that equal the other function, 2 times 0? Well, again, 0 equals 0. Check mark. Yes, it is differentiable for that reason. Any questions? Okay, good. See, we actually just solved that problem in 1 minute. That's like record time for me. I also probably went a little fast there. So if it doesn't make sense, again, you can watch the recording. You can write in the comments below. You can shoot me an email. And I would be more than happy to answer your questions. Now for the last 2, we need to find the values of c that satisfy the mean value theorem of f of x over the interval. If you remember, you first have to check that it's continuous and differentiable very first, okay? So this is definitely going to be continuous because this function is continuous everywhere. There's no values for x that are going to break x cubed. I promise you that. Now let's take the derivative, f prime of x. Well, f prime of x, that's 3x squared. And that's fine. That's differentiable everywhere because there's no values that are going to break the function. So I'll give you a second to catch up with the writing. But so far, we've passed our checks, and now we can use the mean value theorem. This is all we're saying. Okay, moving on. So if you remember what the mean value theorem says, it's f prime of c. That means 3c squared. I just replaced my x's with c's. Really not a big deal. If you want to leave it as an x, I'm not going to stop you. I really don't care. But technically, it should be c. Equals f of b minus f of a. That means plugging in 0 and 2 into x cubed and seeing what those values are. So for instance, 0 cubed is still 0. 2 cubed, that's 8. So in other words, in my numerator, it's going to be 8 minus 0 divided by the x values, 2 minus 0. So it looks like we get 3c squared equals 8 divided by 2, which is 4. This one's going to be annoying. It's not going to be a pretty answer, and that's okay. But next we have to divide by 3. So c squared equals 4/3. And then we take the square root. And please, please, please remember, whenever you take a square root, it's plus or minus. I cannot tell you how many times I have to tell my students this. So the final answer is c equals plus or minus. We know the square root of 4 is 2, and we do not know the square root of 3, so you'd have to leave it as a square root of 3 in the denominator. And technically, we're not supposed to keep square roots in the denominator because our teachers say so. And so what we do is we have to rationalize. If you remember rationalizing, That's where you multiply by root 3 over root 3, like this. And you'll get c equals plus or minus 2 root 3 over 3, because the square roots cancel in the denominator. And this is our final answer for that one. Any questions? Okay. And now just one more to go. It's actually not the hardest one of the night. It's not too bad. We have f of x equals sine x over 0 to 2 pi. Okay, now we have to think. This is not a polynomial anymore. It's not x squared. It's not x cubed. We actually have to think, is this continuous everywhere? Can someone tell me if sine x is continuous everywhere or not?
Yes, I think sin x is continuous because it's just like a curve without any like places you crash.
Very good answer, because sine x, if you think about it, is just a curve like this that goes on forever. There's no values of x that are going to break it. By the way, the same is true for cosine, so you'll see why that matters in a second. But f of x is going to be continuous everywhere. That's good, because that means I can use mean value theorem. And by the way, let's say hypothetically that sine x was not continuous at 3 pi. Let's just make up a number, 3 pi. Would that be a problem for us? No. Why not? Because I'm only looking at 0 to 2 pi. 3 pi is outside of my range. So even if it wasn't continuous everywhere, there's still a chance I can use the mean value theorem as long as it's continuous within my bounds, 0 to 2 pi. So that's good. Next, we have to find the derivative, which hopefully you know by now. Derivative of sine x is cosine x, and like we just said, that's continuous everywhere as well, except we have to say the word differentiable instead of continuous. And so there we go, it's differentiable everywhere. And so now I will finally say that we can use the mean value theorem, so f prime of c, in other words, cosine of c, which looks ridiculous, but whatever, equals f of b minus f of a. This is where I plug into the original function. I have to say what's the sine of 0, and I know that's 0. And then I have to say what's the sine of 2 pi, which that one's harder, but I know it's still 0. And hopefully you know your unit circle. If not, then I'm just helping you right now, obviously. So the numerator will be the y values, 0 minus 0. The denominator is the x values, which is 2 pi minus 0. So it looks like the cosine of c is going to be 0 over 2 pi. Anything divided by, well, 0 over 2 pi, that's still 0. Because whenever you have 0 in the numerator and some number in the denominator, you're just going to get 0. So now I need to solve for c. I'll give you a hint. The answer is not 0, actually, which is funny. But the reason why is because if you think about it, I have to solve for c by taking the arc cosine of both sides. In other words, the cosine of what angle equals 0? Does anyone know this? The answer is...
Is it pi over 2?
Pi over 2 is one answer. There's one more.
3 pi over 2.
Yes. Now, technically, it's also 5 pi over 2. It's 7 pi over 2. You can have fun with this. You can go on for a while, depending on how much paper you have. But remember, what were our bounds? Our bounds were 0 to 2 pi. And so for that reason, I can't go past 5 pi over 2, 7 pi over 2. I only have two answers. It's these two right here. Anything else would be past that. Oh, and by the way, in case you're wondering, what does the mean value theorem say here for this example? Which, again, final answer, I have circled, we're done. But I just want to show you an added fun surprise, which is what's going on here. So here's the graph of sine x from 0 to 2 pi, right there. Here's 0, here's 2 pi. What I'm saying is, if I connect the dots from start to end and draw this red line right here from start to end, just like that, close enough, then the question is, where does the slope equal the red line, which is flat? It's a flat slope. You would say the slope of my sine graph is 0 at 2 points. The slope is 0 right here, and the slope is 0 right here. Coincidentally enough, at x equals pi over 2 and 3 pi over 2, proving that the mean value theorem works. And there we go. So again, we covered chain rule, differentiability, and mean value theorem today. Next week is probably going to be my favorite lesson of the 8-week course because, well, maybe not my favorite. They're all my favorite. But I really do like next week because we're going to be talking about something called critical points, and we're going to be finding relative extrema, which is a fancy word for maximums and minimums, and you're going to see that that's actually pretty cool. So thank you all for attending today. Please do the homework and stay on top of it, and I will see you next week. Take care, and bye-bye.